And with that, I want to bring up the first FDL team, which is going to talk about lunar resources in a project we call the Moon for Good. So team, if you want to come up and take the stage.
Okay, hi everyone. So yeah, we are the Moon for Good team. My name is Nikki. We have Valentine, Jerome, and Ben here, and we've been studying lunar resource mapping this summer. Before I tell you about the work we've been doing, I just want to make sure to say a really big thank you to our mentors who really helped us out a lot this summer, and we're really grateful for all of their support. So humanity is going back to the moon. We recently had the 50th anniversary of Apollo 11, and now with the upcoming Artemis program, NASA is going to lead the way into a new era of lunar exploration, with plans to put the next man and the first woman on the moon by 2024. But not only is humanity going back to the moon, but we are going back to the moon for good. With plans to build a long-term permanent lunar base, humans are going to be there to stay. And in order to really achieve this monumental feat, a significant amount of resources are going to need to be dedicated to the lunar surface. Now, it's really difficult and very expensive to send resources from Earth to the moon. So it's crucial that we understand what resources are available to us existing on the lunar surface. So metal is going to be a really key resource for these sorts of missions, and metal can actually be deposited on the surface of the moon in the form of metal meteorites. So this is an image taken by the Curiosity rover on Mars. And this is essentially just a big chunk of iron and nickel sitting on the surface. And we've actually found similar sorts of meteorites here on Earth. So if we can find the location and find a way to detect where these metals are on the lunar surface, it would be a really big step forward in our goal to build a sustainable lunar base.
The problem is nobody ever attempted to detect these objects on the lunar surface. What you see here is a crater called Tycho on the near side of the moon. Tycho is quite massive. It's about 80 kilometers across. And to put it into perspective, we added the Golden Gate Bridge and a white circle here. It's quite small, as you can see. Tycho is also very deep. It's about 5 kilometers deep. So it means that Tycho is deeper than Mount Whitney in California is tall. And even with this amazing image you can see here, we're not able to distinguish a metallic object on the surface from a normal rock on the surface. So we need more data and more information to do this comparison. And we solved this issue by collecting data from 6 international different spacecraft, a big data stack, including 12 different instruments that cover different portions of the electromagnetic spectrum. So we cover visible, ultraviolet, we cover microwave, gravity, gamma, we call magnetic and thermal instruments. And by combining this data, we are able to distinguish a metallic object from a rock, for example. And this means that we can have our amazing imagery and combine it with, for example, an elevation model that gives us information about the relief of the moon, the terrain of the lunar surface. So blue colors indicate low elevations and brown colors indicate high elevations. We can also use maps like a rock abundance maps, where red colors indicate rocky regions, so regions that are very blocky, and blue colors indicate regions that are quite smooth, so they are not very blocky in that sense. We can also use maps like the surface temperature. Here, red colors indicate hot areas, and green and blue colors indicate cold areas. And by combining these different data sets, by stacking them, by fusing these data sets, we can create a data set which is very powerful for machine learning-based anomaly detection on the moon.
So the aim of our project was to find metal signatures on the surface of the moon without exactly knowing what these metal signatures look like. So we approached this problem by using our computing power to look for general patterns in the data that we have from previous lunar missions. And we decided to just focus on those maps of the moon that tell us something about the optical, thermal, and magnetic properties of the surface, because these are the properties that we believe are most closely related to these metal signatures. And what we found from our analysis is that we could isolate 7 distinct patterns in that data, each of which is related to a different anomaly. And when we say anomaly, what we mean is that one area of the moon might be particularly bright, or it might have a very strong magnetic field, or it might be very hot, and so on and so forth. And to give you an example of this, in this slide, we show you 7 different craters where we detected some of these anomalies. So, for example, we have Marius A, which has a very bright center in the visible range, but that is not as bright in the infrared range. Or, for example, Hell Q, which is overall very bright, but which has a very bright center with a magnetic anomaly in it. And then we have Geodama Bruno, which has a bright center but quite dim surroundings, or also Galois, which has a very strong magnetic anomaly. And what you can see from this example is that we can use these anomalies to distinguish between different craters. And that is very exciting because it allows us to create a crater catalog that we can use to classify craters. And we think that this is a very powerful result because once we found a certain metal in one of these classified craters, it will immediately inform us about the likelihood of finding the same sort of metal in all the other craters that are in the same class of our catalog.
So a very specific way that we think we can search for metals on the surface of the moon is to look at the temperature of the moon. So metals are really good at absorbing heat. Imagine if you're sitting in your car on a hot day and you accidentally touch the metal part of the window or the seatbelt. It's super hot. So metals are very good conductors of heat. And we think the same thing happens on the moon. So we expect to see the variation of temperature throughout the lunar day for metals on the surface to be very different to their surroundings. So what we did is we gave 35 terabytes of existing thermal data on the moon, and we generated, we gave that to an AI, and we trained it to detect these types of anomalies on the lunar surface. So what you can see on the right-hand side is a map that is generated by our AI that tells you where it thinks there's likely to be these types of thermal anomalies. And it's a really interesting map. You can see there's bright spots, and that's where it's indicating these types of high thermal anomalies. And we see there's a bright spot in the center of the crater and also on the western rim. So we think this could indicate the presence of metals. This is really interesting because we can't see this on just the visual data. And so this AI generated map is really helping us to search for these resources. So we are really excited to be working in this area. We are part of a younger generation who haven't seen humans land on the moon. And we really want to see that in our lifetime. So we are leading a new paradigm of AI-driven lunar space exploration. And we think AI is really enabling this kind of big data fusion, resource mapping for the moon. So these are some really amazing images of some of the craters on the moon. The moon may be a really hostile place today, but imagine what it could look like in the future. Thank you.